Start coughing, don't worry. It's not contagious. I've had this for like 2 weeks. Not really cool. Okay, so my keys on a string. Here's the string. I spin these things around at a constant velocity. My question, was there acceleration? Well, what's our definition for acceleration? Change in velocity over change in time, but it's usually just some time I give you, 3 seconds. We assume it starts at 0, right? So change in velocity. Remember, velocity is a vector. It has magnitude and direction. This is a constant speed, v, which actually stands for velocity, but that's fine. Okay, so the magnitude might be the same, but direction is always changing, isn't it? So yes, it is accelerating. There is acceleration. Okay, even though the speed remains the same, the direction is constantly changing. So yes, there's acceleration. So where is this acceleration? If I look top down, okay, because we're just going to do horizontal here first. There's v. This acceleration is always directed towards the center. That kind of makes sense? So as it's out here, well, there's something causing it to go that way, right? And as it's over here, there's something causing it and around and around and around. So it should kind of make sense, and if not, well, I just told you. So that's a special acceleration. We call it c for, centripetal. And I know everybody wants to think about centrifugal, centrifugal. There is no centrifugal here. Centrifugal means to the outside. There's no outside here. It's to the inside. Okay, and it's Latin again. It's center. Centri means center, towards the center. Okay, and pedal I think means inwards or something. I don't know. Don't quote me. Right? That's centripetal acceleration, and here is a formula. It's v squared over the radius. And don't ask me where it comes from. I'm not deriving it here, but there's something to do with similar triangles. Okay, and assuming an arc is just a straight line and this and that. Feel free to look it up if you're really curious. So we don't write centripetal every time. Excuse me. It's just AC. Okay? And that's on your formula sheet. So that should kind of make sense. The faster v is, it's the square of v, right? We know the bigger the acceleration as a vector. If v is really big, well then a is really big. And the radius has to, that's an inverse of the radius here. So the larger the radius, then the smaller the acceleration. Okay, so mathematically, you should look at that and kind of make sense of it a bit. Okay, so that's centripetal acceleration. Also, we know this formula. Okay, so that also applies. That's Newton's second law. Force is a product of mass times acceleration. So if the acceleration now is centripetal, then we also have a centripetal force. All right, and we know, I don't know if you know this old, was it David and Goliath? Okay, where it's a myth, it's a Greek myth, it's a fantasy tale. But anyway, how did this 5'5" man kill this 18-foot beast creature giant guy? He had a little sling with a rock in it, and he spun it around and around, and he lets go one half of it, and the rock hits the giant and square in the, not in the temple, which is a soft spot, but anyway, it hits him right square in the forehead, and he kills the giant, right? So the faster I swing this thing, the larger the force if I let my keys go. Okay, so kind of makes sense? Just Newton's second law. It's just centripetal. Okay, so this just seems a little bit weird because before, and everything else you've done, acceleration and v were in the same line. I'm not going to say same direction because you could have a car going that way and a negative acceleration, but they're all in the same dimension, right? So now they're right 90 degrees to one another, which is kind of weird. All I can say is that's what's going on. Okay? So, centripetal acceleration. If I do let go of my keys right there, or if this rope breaks, okay, or if this is a car going around a corner and it suddenly hits ice and breaks traction, what direction is this going to go? Is it going to go like that? A, B, or C? Now remember, you're looking down on this thing, okay? Maybe it's a train and it ran out of track. The track was holding it in this arc, this circle, causing it, okay, the force of the track on the train wheel is causing it to go towards the center, and all of a sudden, no more tracks. Who likes A? Who likes B? And who likes C? So a wide variety of choices here. Well, this is curved. Remember, we're looking down on this thing. This isn't vertical, okay? I know if I let it go here, gravity's going to suck it back down. If I let it go on the top, I'm just looking down on it, so there's no gravity effect. After this tension breaks, what are the forces on the keys? Is there anything causing it to curve here? The answer is B. It'll just go straight. Okay? So I just got one example. Let's do something practical. Earth. Well, I'll write it the way I have it. Earth travels around the sun. There's a word for that. What do we call it? Orbit. Yeah. Orbits the sun. I could say that too. So the radius is 1.5. Excuse me. Okay, the orbital radius of Earth around the sun is pretty darn big. 1.5 times 10 to the 8 kilometers. What speed does Earth travel? And what is the centripetal acceleration? And finally, centripetal force. So today, that's basically the type of question you're going to get. Some conceptual ones, and some circle stuff. Oh, here's good old Earth. Some of you guys were down here getting tattoos. Okay. Here is. That's the sun. That's Earth, yeah. See that dot? That's where bad guys go to get tatties. So, Earth goes around Sun? We kind of know that, right? Or is it the other way around? Careful, I'll put you in jail. Think before you make your choice. What speed does Earth travel around the Sun? So we know, I've told you, Earth does several things. You guys are all moving in several directions right now, right? You just don't feel it. So, what do I know? I know that. Speed is what? V. So I need to get that before I do this, right? I got a radius. Do I want that in kilometers? No, I don't. So that's a factor of 3 more to make it in meters, right? That's how I want it. 1.5 times 10 to the 11 meters. Right? 1,000 meters in a kilometer. Speed. How do I find this? I'm assuming that's a constant speed, right? So if I know the distance and I know the time, then I know the speed. What is the distance that Earth goes around the Sun? We are going to make an assumption here. It's actually an ellipse, but we're going to assume it's a circle. What is the distance of a circle? That would be the area. Circumference. That's what we're looking for, right? Yeah. So that's the distance Earth goes. R being 1.5 times 10 to the 11. This thing doesn't like writing near the edge. Now, if I only knew the time it took for Earth to get around the Sun. Who knows that? Anybody ever learned that? Yeah. You have? What is it? A year? Is that how long it takes? Does it take a year? I want that in seconds though, right? Let me actually move this a bit. It's a year. Which is 3, we're going to approximate this too. It's not 365 days. We're going to approximate it. 365 days. How many hours in a day? Did you say 25? And how many seconds in an hour? How many seconds in an hour? Okay, that's the speed, right? What do you get? 2 pi times 1.5 to the exponent of 11 divided by 365 divided by 24 divided by 3,600. That should be in meters a second, right? Do you feel it? Hang on. It's pretty darn fast. So 29886 meters a second. Times it by 3.6, that's 100,000 kilometers an hour. That's how fast we're all moving right now. Okay, that's the speed. That's A. B, what's a centripetal acceleration? Well, once I have this, I plug it in there, I square it, I divide it by the radius, and that's a huge speed, so I should get a huge acceleration, right? Not so much. So we don't really, we are acceleration. You can be assimilated. That's the acceleration. You should be able to feel that because that is a change of speed. But that's pretty darn small, isn't it? 0.006 meters a second squared. So there are some tools that could actually register that, but that's 10 times the acceleration of that, right? Just me moving like this and this. So, and of course we're born here, we've been accustomed to this. I think if the Earth started spinning the other way around all of a sudden, going the other direction around the sun, we'd probably all get a little bit dizzy. All of a sudden you start feeling this, right? Anyway. So AC is 0.00. Whoop. What are the units for acceleration? Yeah, just because it's centripetal doesn't mean it's anything different. Finally, the centripetal force, M, A, it's just centripetal. So when I'm talking the force, what mass do I want here? Force on you, force on Earth? It's Earth we're talking about, right? What's the mass of Earth? 5.98 times 10 to the 24 kilograms times that. Pretty big force. Exponent of 22. Newtons. So you wouldn't want to be standing out in space in the way of this thing, would you? It might just move you out of the way. Or would it suck you in with its immense gravity at 9.8 meters a second? So I'll give you the questions, and actually I just thought of something I read the other day. 1 to 11 on the worksheet. There was, someone just came out, he's actually from McGill,